Nice to meet everyone. My name's Yang Tian. I'm the VP of Product at MemVerge. I wanted to go over a little bit of under the hood and advanced use cases for App Capsule. Before I start, I just want to have a quick review. I think earlier in the presentation, Charles introduced the concept of AppSol, and then Ravi went over our first fault-tolerant service based on the AppSol capabilities. Now, let's get into the meat and the sauce of it. I think actually this is App Capsule is not easy to build. There's actually a lot of challenges, and I have to thank Rico earlier for his question because I actually had to flip to this slide to make sure I cover everything that Enrico had asked for. So there's basically we can break up these challenges into three categories. In terms of completeness of the information that we have to capture, being able to do it at reasonable performance while we're capturing and restoring those information, and do it transparently, so that so it actually works well for the use cases. Now, first going to a bit more on the completeness. I think like as you guys all know by now, like the application states, they're everywhere, right? They're in the registers, they're in the cache, L0, L1, L2 cache. They're in the memory. There could be file handles, could be socket information. They're in the storage. I mean, traditionally, that's what people look at. That's the biggest amount of information. It's in the storage. But what you may not realize is they're also in devices. They could be in the accelerator like GPU, or they could be in something like a SmartNIC, MPI applications, which are very popular in the scientific world. There's state information in these smart network interface cards. They're in the cluster. That was one of the questions I think Ravi answered earlier. Like your applications, if you're running a cluster application, it could be on the node of the worker, or it could be in the cluster manager nodes. They're in the cloud, right? That's what we're talking about here today. Big memory cloud, the information are in cloud. So it's everywhere. We have to capture all this information, being able to restore it. We also have to do it synchronously, because otherwise, if these things are out of date, like out of sync, like Charles mentioned, this is a very powerful technology. If they're out of sync, you would get application crash. The next up is in terms of performance. And then this one, like it's, I would break the overhead into several dimensions. So dimensions is that like these overhead are in terms of both execution time of your application, memory overhead during this process, and to some extent storage overhead as well, although nowadays storage is cheap, so it's not that much of an issue. Other dimension of this overhead is that these execution time overhead could be occurring during the runtime. Like with our memory machine, we might be incurring overhead during the runtime, or we could be incurring overhead during the checkpoint and restore process itself. And if you map everything down to more traditional kind of the snapshot restore metrics in the storage world, it's RPO, recovery point objective, and RTO, recovery time objective. Recovery point objective, make sure you don't lose information during this process, or you lose as few as possible. And then RTO is the amount of time or overhead it takes to recover, so you don't lose time again. So shorter the better in both cases. Transparency. So now we know it works well, but is it usable? So we want to make all these work transparent to the end user. First of all, they don't have to worry about switching spot instances. That would be a bit difficult. It has to be transparent to the application, and not just the application itself. Because nowadays, a lot of these applications are part of an entire automation pipeline. There could be workflow manager involved, Airflow. There could be job resource scheduler involved. Could be Slurm, IBM LSF, very popular in the scientific world. I think there are some questions about the runtime environment. We could be talking about containers, VMs, bare metal, right? And then like on top of it, there's orchestration on top of that. There could be OpenShift, Kubernetes, or some other ones that we haven't seen yet. And then even more so on the cloud side, there's cloud services and cloud resource managers that manage the provisioning of these VMs that we have to work with. These could be on the AWS side. There's a Spot Fleet, for example. So this is all kind of this is a overview of all these constraints or problems that we have to solve in order for this app capsule to work.
Okay. I have one question,
sure.
Real quick. I don't know if you mentioned already, but where is the sort of manager running to orchestrate the, spinning up the new Spot instance, copying the memory over, making sure it's loaded properly? Is that running as a service from you, or is that something that I run as another EC2 instance in my AWS account?
So there's a multiple levels involved here. This is as in any stack. Right, at the VM level, we will work with like Spot Fleet to actually provision the VM instances. On the level above that, we will work with like a job scheduler to figure out how would you match the job with the resource, right? Like it could be running an app, and then you have Slurm or something to divide between the multiple VMs. We will work with these kind of managers. Our system is we call them coordinators. It's actually, it's a framework. This is a slide that I think hopefully answers your question.
Okay.
So what, let me maybe back it up, and I promise I'll come back to your question.
Okay.
So this is a kind of a slight addition to what Charles has shown earlier in the presentation. The under hood is this coordination framework. So what happens now? Like traditionally, I think Charles mentioned earlier, our focus has been in this in-memory enterprise class data services. And then what we do, our special sauce, is to be able to capture all these information in memory, register cache memory. And then we've been able to do that in a very fast way because of our magic at these two layers. With the app capsule, what we're introducing is this kind of a coordination framework. And then coordination framework, let's say if we look at a single node that's on this side, coordination framework will coordinate with a storage snapshot, right? So like one example is maybe not local, but EBS. Let's say if you have a AWS EBS attached to this particular compute instance, we will work with EBS to snapshot the storage that's associated with this job. We could also work with NetApp. So we don't do the storage snapshot ourselves, but we would coordinate with the snapshot system that's actually run. We can coordinate with the application. There was a question earlier, is like, do you snapshot transparently to the application, or do you need application changes? The answer is both. Like if you wanted to use it in a transparent mode, that's easier. We support transparent checkpointing. But if there are some things that in the application state, you want to run to a particular pipeline stage and then snapshot, that's okay too. We provide the API to do that. Then the cluster managers. This is where if you have multiple nodes that's running, it could be like an in-memory database, could be Redis, could be Hazelcast, right? So how do we capture each one of those worker nodes without disrupting the cluster's work itself? This is how we would integrate with the cluster manager. Likewise, we have things on the other side. I'm going to step over here. We will work with the cloud services. We will work with the workflow manager. These are kind of like the Airflow or job schedulers and services specifically like the cloud resource services, like Spot Fleet.
Mm-hmm.
So when I say we work with them, what we do is that we catch the signal of what they're about to do, and we plan on what we plan to do. So we make sure these two don't cross paths together, because there is a chance that, let's say we've been running this job that Ravi has mentioned. It's a 2-week long job. It's being scheduled through Slurm as a job scheduler. Slurm detects that the node failed, comes back to Slurm, says, hey, I'm going to launch a new node. I'm going to launch a new Spot VM, and then restart the job from beginning, which is bad. So what we do is we actually intercept that signal from AWS saying this VM is about to die. Instead of launch a new VM from the beginning, you launch it from the last checkpoint. So that's essentially how we do it. Does that answer your question? It's a roundabout way, but
I think so. Yeah.
Okay.
It might be clearer once we see the demo, I think.
Okay.
Yeah.
Okay, cool.
I have a question. In particular, how much work do you need to support a new, cloud service provider and all the other components that are, listed in this slide? Because there are several job scheduler, workflow managers, cloud resource manager in the world, and so on. I mean, also the matrix to have all of them. It's
there is some integration work involved, and I think that's actually part of the complexity. When we build this framework, we're building a modular fashion. So we have part of the framework that will work with the job scheduler, and then we have plugin to support either LSF, IBM LSF, or like a Slurm, for instance, or AWS Batch. So, and then as part of the plugin, some of the work sits in with our memory machine. Some of it are sample code that the user would have to put into their batch configuration code or Slurm configuration code. So just to answer your question, it's true. Like there is some integration work involved, but we have tried to take kind of a more framework approach so that the integration work is not overwhelming. Once it's done, it will work automatically. Next slide. I wanted to show some use cases, more advanced use cases that we have done in our as proof of concept with a customer. Again, you see a lot of genomics, because that's I think that's because the nature of these jobs. These are like huge computationally and memory intensive jobs, and then they need this type of help the most. So this particular job, it's a gene assembly job. You can see like this is a memory consumption. It runs over 14 days. Most of the time, it's about 1 terabyte of memory usage. For a short period, it spikes up to 2 terabytes. So previously, what happens is that a lot of times this analysis is not done because they don't have a machine that can support the 2 terabyte DRAM, or they couldn't find time to do it. What we came in is we saw the profile, and instead of running the entire workload on a 2 terabyte capable machine, what we did was we took a snapshot. We ran this application on a smaller, it's a relatively smaller 1 terabyte machine until right before it spiked. We took a snapshot. We moved the workload without stopping, without interruption. We moved it to a larger 2 terabyte machine. We were able to run it on the 2 terabyte machine for a shorter, on larger machine. It's actually probably 4 terabyte machine. We ran on the bigger machine for a shorter amount of time. When it's no longer needed, we took a snapshot and then brought it down to the smaller machine. Now, because this is a POC, we actually had the freedom to try a number of things. So we tried on-prem. We took a snapshot. We used RDMA to take this entire snapshot of memory, because the memory actually, the snapshot of it is pretty big. It's 1 terabyte. So it actually is pretty big. So we use the RDMA to take it to the bigger machine. We also took this memory snapshot. We used S3, and then we were able to burst to AWS as well. So we try multiple iteration of this. And the reason I like this example is I think I'm trying to illustrate a couple of things that we can do with our technology. One is to increase the flexibility of your job, where you can run your job, so you can run it faster. At the same time, you're increasing the utilization of your resources. So you don't have to be like wasting 1 terabyte on that big machine. You can bunch up really big jobs with that. The second part, so that part is about like right sizing, right? We're actually right sizing the job we're right sizing the machine to the job that's most suitable for. The second part of it is a case that Charles mentioned earlier, the cloud bursting, right? A lot of times this organization that we work with, they happen to have the funding to have these big machines, but we have other customers who don't have these big machines on site, and then they don't have the big cloud budget as well. So this is a perfect example of where you run the job wherever you can on the cheapest, whether it's on-prem or in the cloud. And when you have to, you use like the lowest cost alternative possible.
Quick question on this, and I don't know if it's possible, but are you able to even compress the snapshot as you take it? So you wouldn't even need the 2 terabyte machine while you take the snapshot. You have algorithms that can do that while you take the snapshot?
It's something that we're working on. So we want to do this really fast. So like when we're taking a snapshot, that may not be the time to do it, but when there's a post-processing step, and that's where we're actually actively looking into those kind of systems. Yep. Okay, any other questions? Okay, so let me move to the second example. A second example is a different customer, same problem. What happens in this case is that they also have a large job that will require multiple days to run. And then like their own data center is actually, if you look at the utilization of their data center, is actually pretty high. So normally it would take them a month to wait for that larger block of time to be available so that they can run their job. With our app capsule technology, what we're able to do is essentially time slice this one large job without the application actually changing itself. So we were able to take 1/2 the workload. It's not exactly 1/2, but then for illustration purposes, we took 1/2 of the workload. We were able to fit into like a downtime or like a valley of the utilization of their servers. We're able to run 1/2 of the job during this period, and then we were able to run other half later on. So we were able to run this job rather than waiting for months to do it. In reality, we actually broke it down into like 4 to 5 chunks, and we were able to run that job during the downtime of the system. I'd like to introduce my colleague, Eric, for a true demo.
All right, hi, my name's Eric Lasota, and I'm the Senior Systems Engineer at MemVerge. And I just want to say that what I like about doing demos is that it's a lot easier to understand when you can see it than when you hear it, especially when a lot of the things that we're doing especially are really new. And so I make the engineers demo their stuff for me, and that way I can understand it better. You may be a little disappointed because it's so much easier than it sounds that the demo is very short. But the first thing I'm going to do is describe what I'm going to do so that I won't be stepping on myself during the actual demo. Essentially, what we have is a multi-stage data analytics application, and we're going to start it on-prem, and we're going to run through iterative stages, taking a snapshot at each stage, and then we're going to stop it and replicate that snapshot into the cloud, burst it into the cloud, and immediately restore it and start up again. And because these are in-memory snapshots, the taking of the snapshot and the restoring of the snapshot is less than 1 second, and it works. So this is the screen that's going to be up when we're doing the demo, and I'm just going to explain a little bit. So again, the blue terminal session is my local machine on-prem. The white terminal session is the virtual machine in Azure. We're doing it in Azure today. The browser has 2 tabs. One is running RStudio on the local machine, and the other one is running RStudio on the Azure machine. That is what's going to happen in the demo. And because I like things to go really smoothly, I recorded the demo so we could just watch it, and I'll talk to it as it goes. So what's going to happen at the very beginning is RStudio is up and running, and we've run the first iteration of this graphing program. You can see the result is in the bottom right corner there. And we're going to go ahead and start taking our snapshots. So, that's starting? Yes. So the first thing we do is we take a look and we see that there are no snapshots. We identify the process ID that is the application itself, and that's the 92735. I don't know if my text is good enough to read. But so I wrote a little script for the command line to take the snapshot to make the demo go more smoothly. But essentially, I just say take a snapshot of this process ID, and it took 0.2 seconds. Then iterating the program to the next step, we see the graph has changed. Come back, create the next snapshot, and again go back to RStudio and run that third iteration through. Take a third snapshot. Now, just stopping RStudio, I'm listing out the snapshots, and you can see that they're persistent. They've been written to persistent PMEM in this case, and now I'm logging into my Azure VM, and I'm listing out the snapshots so you can see that none exist at this point. So going back to my on-prem system, I had to prove to you that I had an actual Azure VM so you guys would believe me. So 111 is the IP address of that VM. So I go back, and up here on the blue terminal session, you'll see I'm running a replication script. I'm copying that snapshot to the Azure VM, and this takes a second there. I'll let it go through. Completed, and now I'll run my list again, and you'll see that it now exists, and you'll also see that it has the exact same name as it did on the local machine. So now that you can see that they're there, we're going to switch the RStudio tab from the local machine to the Azure VM. And what I want to point out to you is that when you do, you'll see that RStudio is running, but the program's not running. It's just up. RStudio is running, and there we go. So RStudio is running, and I go back to, I don't know why I refreshed it twice, but I go back to my Azure VM, and I run a command to restore the snapshot. So I copied it there. Now I'm restoring it into memory. Simple command, and it's done. Go back and refresh my Azure screen or RStudio, and you can see it now is back. The graph is visible as the one that was there at 3. And now I'm going to start iterating through, picking up where I left off. And that's literally it. And I have a few more seconds of me iterating through the graphing program, but that is literally how simple it is. It took these guys 2 hours to explain it, and it took a minute and a half to demonstrate it, but a lot of work went into making it simple for people like me, actually.
So can you go through some of the metrics here? Like how much was the data restored? What size of the machines? Just high levels.
So for this particular instance, it's relatively small,
Yeah.
right? So, you know, the iteration through the application could be quick.
Yep.
And if you had a much bigger application, which you're very likely to do, the snapshotting is equally fast, right? Because it's in memory, and so it's very fast, less than a second. The transmission of that snapshot to the cloud is dependent on
Everything.
the physics of what's going on. And so if you have a super fast connection, you know, most enterprise environments have very fast connections to the cloud, because they're doing stuff there anyway. So it won't be an exceedingly long time, but it's sort of outside of our control. It's
Yes, absolutely.
but once it gets there, the ability to restore it is still less than a second because it's in memory. So a lot of the value, from my perspective, is that the things that used to take a long time can be greatly shortened. So, I have restored an entire environment after an earthquake for 13 hours, right? Yeah. So that was crazy. And it was like is less data than I have on my phone now. So with this, you can get it in, depending on what you're doing, it will take more time. I'm not going to try and trick you about that, but that's physics. But the other thing is that you don't have to do anything. It recovered the process ID, it recovered the application state, everything's there, not just the data. And so the ability to burst up to the cloud because your environment has limited resources. I remember when you had to build for the worst case of the year, right? So year-end calculations, that's how big your data center was, and the rest of the year, you ran at 25% horsepower. That's no longer necessary, and this allows companies to be super flexible. So you can say, hey, I've got to move stuff up to the cloud because we got a big project coming in and needs the on-prem resources or something like that.
So I'm sorry, go ahead.
May I?
Yeah,
thank you. So it was when you made the snapshot.
Yeah,
you were using, there's an agent running on that machine.
Yeah, memory machine software is running on it. Yeah.
And what are you invoking to make that snapshot? Is it a command line tool or?
Yeah, it's actually a command. Remember when I listed the snapshot, it said MVM CLI?
Yeah.
That's our CLI.
Okay, that's your.
And so there's a couple of commands, and to make it easy on myself, I wrote a little script too.
Gotcha.
But I could get you the commands if you would like them.
When you were transferring that snapshot up to the Azure VM, that's also running the agents.
Yeah.
And is that transfer being initiated through the CLI, or are you just doing like a robocopy? Or
I'd have to go back and look at my script because I actually did that a while back, but it's basically a copy, a normal SCP type copy.
Okay. Mm-hmm. I just want, if it stays in memory, pulls across the wire, and is it loading directly into memory, or is it loading onto it?
Well, if you have a DRAM only solution, then your snapshot will be on storage. If you have persistent memory, it'll be in the memory. Okay. So if you're on-prem and you have that Optane persistent memory or any of the future persistent memories, then you'll be able to pull it off at memory speed.
Okay. And the components of an app that are not in memory, is that something you have to tell the agent about to capture as well? I
did have RStudio installed on the VM so that I could burst it up there. So it doesn't grab the portions that are not being used.
Right. Okay.
Does that make sense?
Yeah. So it's whatever's loaded into memory is what it's going to capture and nothing else.
So it's everything under that process ID is captured and brought up.
Okay. So if you had some other portion of the data set that was sitting on persistent disk that's not associated with the process ID, you'd have to copy that separately.
Yeah, for this particular demo, that's the case. But for our app capsule offering, we do have the coordinator. That's where we would coordinate with the storage snapshot along with the memory portion.
Okay, that makes sense. All right, so you have to orchestrate all of those components together to get a full snapshot.
Yeah.
So I think he actually already asked one. So effectively, you created the instance in Azure before you did the actual migration. So you snapshotted here, applied the snapshot to that. Poof, you're back. You switch the target, and you're up and running. That's really, really cool.
Thanks.
Is there like a workflow methodology for, effectively migrate to nothing? So, and I guess that's going to spur the second question I'll get to here in a second, but I've got it running here. Is there an API that I can hit off of the trigger that says oh no, this is going to fall apart on me. Send this here and just build it as needed.
Like all of it.
Yeah. Like build from scratch. So.
Oh, sorry, just to understand the question, like you're saying like I have a workload, and then you want the orchestration to provision the new VM to take that workload. It's something that so for part of the fault tolerance app, we have built it as part of this integration. So we would work with let's say AWS Spot Fleet to provision a new VM instance, and then we know the new VM instance. We would like put copy our data over to that.
Okay, that makes sense.
Yeah,
and then I guess so is there API capability to it so that it can be, that it can be triggered?
Yes. So we provide both, like Eric saying, like the command line. We also have a GUI interface, and we also have an SDK. So like if your application knows its particular state, it wants to trigger the snapshot, then you can do it through the SDK as well.
Okay, and then final question. So the concept of the bursting that you're talking about, which absolutely that makes sense. I run out of space. This is good. Have a big thing happens. I need to move it here. One thing that Dr. Fan said earlier was what we want to do is we want to move to something the same size or bigger as we move it. What happens when that workload need now shrinks and I want to fail back to that smaller, cheaper workload capability?
Yeah, that actually was a previous case I was showing, like the 1 terabyte.
Okay.
I
saw the video, but it was like these two things don't match. So
so we can do that. So like I think like that actually may be one of the case where you should use the API, because as an app, you know your state better than what we would be able to do.
I was wondering, so when you take snapshots, so you need an exact amount of memory,
It's
all
not
the memory allocated from the application. So if the application allocates 1 gigabyte of memory, you need an additional 1 gigabyte. But if you take multiple snapshots, so this adds up in the end. So do you have a mechanism to organize resources, to use virtual memory or anything else to avoid any critical situation in the machine?
So let me just say that question back to make sure I understood it correctly. So as each snapshot is taken, it takes up a certain amount of memory. And do we have a mechanism to prevent you from essentially consuming all the memory?
Yeah.
Question.
Yeah.
So,
because as far as I understand, it's a manual process to copy the snapshot.
Yeah, so like I think one of our differentiators from previous effort is that because we do all these steps in memory, we do copy and write in memory, for example. So we're not taking let's say if your application is using 1 terabyte, we're not taking 1 terabyte to do a snapshot. We're actually only taking the diff of what happens in between. And then we would offload that in the background into a more persistent storage. So from your application standpoint, we do need to pause the application to take that snapshot. But then once those are marked, the offloading is happening asynchronously. We manage that in the back end. And then we do have various fail-safe mechanisms if you do run out of memory.
Okay, very good.
Yeah, and that's actually how we reduce overhead. That is a big part of this reducing overhead of snapshot.
Fantastic.
so I just want to say that first off, there are many, many videos that are much longer than mine on our YouTube channel and on our landing page. There's one that's essentially a restoration locally as well as bursting. There's a spot on AWS where you can see that it automatically starts a new instance and migrates everything over. So they're available on that. And so I just wanted to say that if you guys have any questions and you want to see a longer demo or anything like that, that's my email address, and you can reach out to me anytime, and I'll be glad to either answer your questions or find someone smarter at me that can, in fact, answer your question.
Well, I got one more question.
Sure.
I'll toss out here. This will be a fun one for y'all to answer. So with all the different things that y'all are doing within snapshotting, actually, let me take a step back, and I think we danced around this, but let's just jump on the horse and beat it till it's dead. What layer of the OSI are these snapshots actually being taken? Are we talking like OS layer, app layer?
So our memory machine works in user space.
Okay.
But we take this, we take all the, we flush the register, we flush the cache. So we have the complete, I think, memory information and everything above that.
Okay.
Yeah.
And so in the demonstration, moving it over to an Azure pre-built machine made sense. And then multiple snapshots after that, if I read that correctly. So there's so many snapshots. A question which sounds really crazy to ask: how does it break?
How does it break? Or?
Yeah, if you have this many snapshots of an application, how does it, like, if you have something that crashes, do you just back up to the previous snapshot and just continue on?
Yep. You could. That's definitely one use case.
My VMware brain is going crazy because you don't take snapshots on top of snapshots. It's like rule number one.
Yeah.
So,
well, each snapshot is independent. It's just at that stage. So if you think back to this, at least this is what I've learned since coming to MemVerge. A lot of our genomics customers, they want to go back to a certain stage and run a different set of variables. And so instead of having to recalculate from stage 1 to get to stage 6, they can just go back to stage 6 over and over again and change the variables and run it again. So, yeah, we're really happy to be the best. So the thing that we didn't touch on, though, is you could take a snapshot and essentially clone it. And we have a customer who runs iterative testing with different variables on the same data. And they used to do it very sequentially. And it took, I think, 6.5 hours to go through all of it. But after a certain point, they come back to that certain point. So we created 4 copies of their data, mounted it up, and they accessed all 4 of those copies at the same time and cut 2.5 hours out of their analysis time. And, they do that over and over again. And genomics companies live and die by their analysis. And so that's a huge savings for them.
That's blowing my mind right now.
I know.
Because I'm thinking about...
That's how I feel every day since I started working.
Like a Monte Carlo style simulation, where you don't have to recompute the whole thing or restore it from something slower or take a full snapshot every time. You can do these in-memory snapshots. Okay, and now I can spread this across 30 spot instances where I can try 30 different variations on it, get it to the next stage, snapshot it again, spread it out again. I'm just the fanning out. It's basically a time machine for memory.
Yeah.
All right, so you have a new log line.
there it is.
There you go.
Yeah.
First one's free.
So when I first started, I got all the input, and I was like, okay, I need to see this actually happen. So we had a server, and I fired it up, and my boss ran me through it, and I'm going like, oh, it really works, because it sounded too good to be true. But it's truly amazing, and seeing it in action is really the most powerful thing, I think.
I'm thinking about like software development and debugging problems.
Sure.
I want to try to replicate different problems from the same starting point. Now I can do that really fast.
Yeah.
So there's another like huge other potential use case that has nothing to do with genomics or anything like that.
So on the cloning solution, our solutions teams had to help the customer split their analysis script into 4 pieces. Mm-hmm. They didn't have to, because they were used to going step 1, step 2, all the way to step 16, I think. But now they just go step 1, 2, and then they run 4 steps each.
Right.
So it's, sometimes it takes a little work to take advantage of the data availability. So
how does one get their hands on this software to try it out? I happened to notice, I was looking around the website a little bit, and I happened to notice you can like request access to a lab, but
you can talk to me. I have lab servers, and we can set something up and and run something? Sure.
I think Yang also has 3 more slides.
Oh, yes.
Yeah.
Yeah.
I think a lot of it actually came out, so it'd be cool. I just want to kind of maybe summarize some of the our vision, and then we touched upon a lot of it. There's a lot of, we're very excited about this app capsule technology. There's just so many aspects of it we can use it for, and I think we're just starting to scratch the surface of it. So a couple of things I wanted to go over in this slide. One is that, you can look at this use case from multiple angles. The 2 angles here, let's say if we look at it from an infrastructure level. So this is for the folks that's running their own on-prem data center or like the CSPs. What we offer is a way to offer to like a guarantee quality of service over unreliable hardware through software. Right? This is the fault tolerance that Ravi was just talking about. The spot instances by themselves are inherently not reliable. But we offer a reliable way that you can run your application on top of that. So this is one way. Other one, I kind of showing the 2 examples, and Eric has shown is we can drive a more flexible scheduling. We can drive right sizing of the application to your hardware. And then therefore we can increase the utilization, the overall utilization rate of your investment. From an application standpoint, we can make any application fault tolerant. We can make it mobile, right? We can just run it one machine to the next machine or burst to the cloud. We ultimately what we want to do is we want to free the applications to run across the space-time continuum, better than time machine in the space component. So, what do I mean by that? This is, I don't know if you guys see the background. This is for the Dune fans. Just came. That's and then like in terms of we call this the big memory cloud space-time continuum. By space, it could be galaxies, but the specific what we're talking about space is the different machines, on-prem, cloud instances, among the cloud, right? So this is what we mean by space. In time, obviously, you know what time is. And then I want to show like several cases. First case I think you alluded to is how do we use this across time, right? Well, like Eric has shown, we take a snapshot at different stages. You can go back to that snapshot. You could hibernate, wait a while to run it. So this is a time app capsule. I don't know, app capsule for time, right? Time capsule thing. You can. So basically, once you have it in this capsule, you can do all kinds of things with it, time-wise. Again, one of the other things, space-wise, you can take it from running on one machine, move it to another machine, and keep it running, right? You can do in-memory cloning. Like that's the case that for your Monte Carlo simulation, right? You run it up to a certain point, you catch all the state there, you can parallelize it later on. So like people do this what if kind of analysis. That's how we try it. So we can. There's just a lots of stuff that we can do with this. It is a big vision. You can't get more than space time. But we're very excited to start this journey, and we're always looking for partners to work with. Because like you can see, there's a big space, and if we're just by ourselves, it's lonely. We want to work with partners. You have this is I want to double take on something Ravi said earlier. This is our first service offering based on this technology, the fault tolerance service. Please take a look. If you're interested, we have an official email info@memverge.com to reach out to, or even better, you got Eric. Like that's a back channel to our service.